We'll begin our discussion of pulleys by looking at an ideal pulley system. This means that the pulley is assumed to move without friction and that the pulley itself is considered to have no mass compared to the rest of the system. Later in the year, we will look at more real pulleys, but for right now, we use the term ideal to represent this type of system. These situations are very similar to the train type problems that we discussed earlier, except that, of course, the rope is stretched around a pulley. So how do we deal with this sort of situation? First thing I'm going to suggest is that you just draw your free body diagram like you normally would for each of the blocks. I'm going to go ahead and use G as 10 newtons per kilogram to make our life a little bit simpler. We have a force of 45 newtons pulling down here. We have tension in the rope pulling up here. For this other object, we have a force of 5 newtons, 10 times 0.5, and we also have tension, but pulling up. Now, I'm going to go ahead and call these two tension forces the same variable, T. Again, later when we work with real pulleys, we're going to have to use different values of tension, but it turns out that if you have an ideal pulley with zero mass for this solid disc, say, you don't need to have forces acting on that pulley to make it move if it has no mass. So by looking at just an ideal situation, we can make the math a little bit easier to work with. The next thing I'm going to do is I'm going to sort of redraw this picture, at least think this in my head, as if there was this system of these two masses sort of combined together being pulled in opposite directions. So what I've done is I've taken this rope that goes around the pulley and I have straightened it out so that it looks more like this. I don't know, maybe it might be better to draw it more like this. That might make more sense, that there is a rope between them, but there's a force pulling the system in opposite directions. So I'm going to think of this more like there's 45 newtons pulling one way and 5 newtons pulling the other way, so that the acceleration of the system would be the net force, 45 minus 5, and then our total mass would be the 0.5 and the 4.5 put together. So that would be 5 kilograms. And then times our acceleration. So our acceleration is 8 meters per second squared. So that's a useful strategy for looking at this problem. Let's take a look at what happens now if tension is what we need. And as we talked about before, you can't find a value for tension by looking at the whole system. It's an internal force, so you have to look at a single object. So we found earlier that the acceleration is 8 meters per second squared, so we'll be able to use that value here. Now, technically, this object, this yellow object, is going to go upwards with a value of or an acceleration of 8 meters per second squared, and the blue is going to go downward with an acceleration of 8 meters per second squared. So I'm going to do something here, and it's going to seem like I'm working against a rule that I've said before, in that you have to choose a consistent direction and use it throughout the problem. But instead of just considering up and down to be positive and negative, I'm going to consider the direction of the rope to be positive this way. So sort of the rope pulling the whole system to the right is going to be considered the positive direction. In this case, then, the weight that was pulling down, the 45 newtons, is positive, and this tension force is negative. So that if I wanted to look at just that part of the system, I could say 45 minus T is equal to that mass times this acceleration that we found of 8. And that would end up giving us a value of tension of 9 newtons. If instead I looked at the other object, this object is moving upwards, and so the tension force is helping the object's motion. The weight of the object works against it. And so in this case, I will consider up to be the positive direction. That is, again, consistent with the whole motion of the system. And so t minus 5 is equal to 0.5 times 8. And again, I get my tension of 9 newtons. Okay, so again, something a little bit different about the system is that we don't just use up as a positive or down as a positive direction. We use around the pulley to be a positive direction, so that forces that help the motion of the system are positive, forces that work against the motion are negative. Let's take another, I'll look at another sort of core problem, this one involving friction and an object on a table. So here we again have a massless pulley, so this is an ideal system. There is friction between the table and the block over here, but there's no friction in the pulley itself. So again, this is considered an ideal system, and we don't need to worry about having some sort of torque that causes rotation in our pulley. We can consider the tension force to be the same throughout the entire rope, even as it wraps around the pulley. So there's a tension force pulling forward on the orange block and pulling backward on the blue block. And you should always see that in your picture. You should see tension forces as internal, so they'll be positive for one object and negative for the other, so that they cancel out when you look at the whole system. All right, other forces that we have in the system, we have a 3 kilogram object, so we have 30 newtons pulling down. And we do have a weight here. Now this weight doesn't actually affect directly the motion of the system. This is not going to be a part of that first step in terms of part of the net force directly, although it's going to help me calculate friction, because if there are 50 newtons pulling this orange block down, then the normal force would also be 50 newtons. And then that's what I'm going to use to calculate friction, of course, that's pulling against. So when I look at this whole system, and I just look at forces that point parallel to the rope, then I have these two objects linked, and there is 30 newtons pulling the system in the forward direction, and then there's this frictional force pulling the system in the opposite direction. Again, the 50 newtons does not show up directly in this calculation. I'm just going to use that to find friction. Friction, of course, is mu times the normal force, so that's 0.2 times 50, or 10 newtons. Okay, so we have 10 newtons here of friction. So if I want to find the net force on the system, again, I've sort of stretched that rope that's stretched around the pulley, I've stretched it out straight so that I can sort of visualize how there are 30 newtons pulling the system forward and 10 newtons pulling the system back. So I have a net force of 20 pulling the full system, so 5 kilograms plus 8 kilograms is, 5 kilograms plus 3 kilograms is 8 kilograms. And so our acceleration here would be 20 divided by 8, or 2.5 meters per second squared. All right, how would we find tension? We would look at the same situation, but just look at one of the blocks. So maybe I would choose to look at this 3 kilogram object that had the 30 newtons and the tension force working against it. For this object, the positive force would be 30. That's helping the motion. Tension is working against its motion. That determines its mass times the acceleration of the system. That gives me a tension force of 22.5 newtons. If I wanted to check my work, I could look at the forces on just the 5 kilogram object. Kind of organize my work here. These were the forces on the 3 kilogram object. So here I have tension helping the motion of this object, and I have friction Remember, that was 10 newtons working against the object's motion. So I have T minus 10 equal to this object's mass times the acceleration. And that would also give me 22.5 newtons. So again, the key thing with these problems is going to be sort of this step here, or the step where we took the rope and we stretched it out straight, and that's how we want to think about the acceleration of the system, and our direction of motion bends around the rope so that the 30 newtons is positive and the tension force is positive for the 50 kilogram object.